In this video, we will learn something about overhanging beam. Referring to these figures, we can see that here we have a beam, but in comparison to a simply supported beam, in this case, it has some extra length. You see, some extra length is here in the first figure as well as in the second figure. Some extra length is there. This extra length from the support is called overhang. So an overhanging beam is one which has some overhang. So by definition, a simply support beam which overhanging from its support is called an overhanging beam. So an overhanging beam must have some overhang portion in this side, left side or right side. Okay, so that is the definition of overhanging beam. As shown in the figure, the overhanging beam may be of two types. Sometimes the overhang portion may be in one side, or the overhang portion may be both sides. These are the two types. Now, another important matter in connection with the overhanging beam is that point of contraflexure. Point of contraflexure. Here I have drawn an imaginary bending moment diagram, and AB is the central line, and the portion below this line is negative, and above that is positive. And one can see that at this point C, the bending moment diagram changes its sign. Okay, so such a point where a bending moment diagram changes its sign is called point of contraflexure. So point of contraflexure is the point where the bending moment diagram changes its sign. Next, we have to solve some numerical problems on overhanging beams. Okay, let us do it. The question given is, determine the load P such that reaction set supports A and B are equal in the beam as shown in figure. Draw the shear force and bending moment diagrams and mark the values at salient points. Okay, so one figure is given along with the question. I have written the figure here. We have to find the value of P. Also, we have to draw shear force and bending moment diagrams. Let us solve it. This is an overhanging beam, and it has a UDL from A to D, and it also has a point load P acting at point C. We have to find the value of point dot P. Also, we have to draw the shear force and bending moment diagram. So in order to solve this problem, first of all, we have to find the values of RA and RB. It is also mentioned in the question that reactions at supports A and B are equal. So let us take RA equals reaction at A and RB equals reaction at B. Also, RA equals RB. Let us first find the total load acting on the beam. That is the load by the UDL and the point load. Total load equals UDL 20 into 4 plus point dot P plus P. But in order to maintain equilibrium, total load must be equal to reactions, total reactions. So this will be equal to RA plus RB. That is 80 plus P equals RA plus RB. Okay. But since RA equals RB, we can write this as equal to 2 into RB. That is 80 plus P equals 2 into RB. Now we can take moments about A. 20 into 4 into half of 4, 2. This is the clockwise moment. That plus P into, we are taking moments about A, so we have to take the distance from A to C. P into 7. That will be equal to anti-clockwise moment. That is reaction at B into distance between A and B. That is 6. Now we can simplify this. We get 160 plus 7P equals 6 RB. Now we can find the value of RB from this expression and we can substitute that value of RB here. When solving, we get the value of P, which is equal to 20 kilonewton. So we got our first answer. P is equal to 20 kilonewton. Next, we have to draw shear force diagram. But in order to draw the shear force diagram, we have to find the values of RA and RB also. But by knowing the value of P, we can easily find the values of RA and RB. Okay, we got the value of P as 20 and RA equals RB. We also know that 160 plus 7P equals 6 RB. So we can substitute this value of P here and we can solve for RB. 160 plus 7 into 20 equals 6 RB. So by solving we can get the value of RB. Okay, we got the value of RA and RB as 50 kilonewton each. Now we try to solve shear force. For convenience, I have redrawn the load diagram once again, and I mentioned the values of RA, RB and P also here. RA equals 50 kilonewton, RB equals again 50 kilonewton, and P equals 20 kilonewton. So now we can start drawing the shear force diagram. Here I have mentioned the values P as equal to 20 kilonewton and RB equals 50 kilonewton. Again RA equals 20 kilonewton. Now we can find the values of shear force at each points. First we consider point C, shear force at C. Shear force at C is equal to 0 because there is no load in the right side of C. Now shear force at B is equal to all load in the right side of B. That is, in the right side of B there is only one load acting, that is P 20 kilonewton is acting downwards at point C. So shear force at B will be nothing but 20 kilonewton only. 20 kilonewton. Here we have to consider the sign also, the sign convention that we use for shear forces. The sign convention for shear force is this is the sign convention we are using for finding the values of shear force. So if you consider the load 20 kilonewton P and the section concerned is at B, the section is at B and the load is at C. Obviously this load 20 kilonewton will be in the right side of the section, right side of B. Okay, so the load P or load 20 Newton is in the right side of the section, meaning 20 kilonewton load is acting downwards. So two things, the load is acting on the right side and it is downwards. So considering these two signs, we can easily see that the sign to be used for the shear force is this one, because here the center line, this is section, and the load, this load is in the right side of that section acting downwards. So 20 kilonewton will be positive. This is the value of shear force at B. And we also have to note that the shear force at this B will be starting from point C. Okay, therefore the shear force at C will be 20 also. Meaning the 0 is in the right side, and from point C onwards up to B, the shear force will be 20. Now, again, if you move to the left side, the shear force at D that will be equal to all loads in the right side of D. First comes this reaction RB. RB is acting right upwards. Obviously that will be this case, so negative, so minus 50. Next load is P, acting downwards, so acting downwards in the right side positive, plus 20. Therefore shear force at D will be equal to minus 30 kilonewton, and this shear force at D will be starting from the point B, or from B to D, the shear force value will be minus 30 only. Now we move on to point A. Shear force at A is equal to, shear force at A means the shear force due to this UDL. What's the value of that UDL? 20 into 4. 20 into 4. And the sign is, since the section we are considering is at A, the load will be in the right side of the section. So right side of the section, the load is acting downwards, so it will be positive. Again we consider RB. RB is right upwards, it will be minus 50. Then 20 means right downwards, it will be positive, is equal to plus 50 kilonewton. So shear force at A will be plus 50 kilonewton. Now, referring to the load diagram, we can see that from C to B there is no load, so the shear force value will be remaining unchanged from C to B, or C to B shear force constant, and from B to D also shear force constant. And from D to A, because of the presence of that UDL, the shear force will vary linearly, linear variation of shear force. Okay, now we found all values of shear force at all points. Now we can draw shear force diagram. I have drawn a line. Now I have to mark the values of shear force. At point C, the shear force is 0, and because of the point load, the shear force is increasing. So we have to mark 2 points at C. I have drawn the shear force diagram according to the values of shear force at each points. Here the shear force is initially 0, and because of the point load it is increasing to 20 kilonewton. then that value will be the same up to the point B, and here there is reaction of B. So because of that the shear force value is coming down to 30. This is minus side. Again that value will be the same up to point D because there is no load in between D and B. And then from D there is UDL. Because of that UDL, the shear force value will vary linearly using a straight line, and at point A the shear force is 50 kilonewton, and we can connect these values by means of a line, and that's all the shear force diagram. Now we can find the values of bending moment and how to draw the bending moment diagram. This is the sign convention we are using for finding the values of bending moment. So we can find the values of bending moment starting from C. So at point C the bending moment is 0. So bending moment at C equals 0 because there is no load in the right side of point C. Now we move to the point B. Bending moment at B will be equal to 20 into 1 meter. 20 into 1. We are considering 20 kilonewton, and the section considered is this one B, and here we can say that the load is acting in the right side of the section, and the tendency of this load is to bend the segment upwards, or that will be a case of negative bending moment. So this will be minus 20 minus 20 kilonewton meter. That is the bending moment at B. Now the bending moment at D is equal to bending moment of all values in the right side of D. So first we consider reaction RB. RB is acting right upwards. Right upward meaning this case. So that will be positive plus 50 into distance is 2 meter. Then you consider the other load 20 into this distance 3 meters, 20 into 3, and the 20 is acting right side of section downwards, so it will be negative minus 20 into 3. So this will be the value of bending moment at D. It will be equal to plus 40 kilonewton meter. Next is bending moment at A is equal to the bending moment due to UDL, meaning total load into distance. This will be equal to 20 into 4 into distance to the center of that beam, of that span. So it will be 2 meter. The load is acting right side of the section downwards, so it will be negative. Then consider RB. RB is acting right upwards, it will be positive, then plus RB. The value of RB is 50 into distance between A and B will be 6. Then comes 20. 20 is acting downwards right. Downwards right means again minus 20 into 7 is equal to, simplifying, bending moment at A we get 0. Note that from A to D the load is uniformly varying. Okay, So in order to find the expression for bending moment at between A and D, we have to make a mathematical expression, which would be a parabolic equation. For that we can take a section between A and D. I have taken a section XX between A and D. That section is at a distance x from the point D. Now we can find the bending moment at the section mx is equal to bending moment due to the small load in this distance x is equal to 20 into x into x by 2. This load will be acting the right side downwards, so that will be minus. Then we consider 50 kilonewton right upwards. It will be positive, plus 50 into 2 plus x. Then 20 into this 20 is in the right side downwards, so that will be minus 20 into 3 plus x. Okay, is equal to 10 minus 10 x square plus 50 into 2 plus x minus 20 into 3 plus x. This is an expression, and using this expression we can find the bending moment at any point in between A and C. Okay, since this is a parabolic equation, we will be getting a parabolic curve between A and D. Now we can draw the bending moment diagram. The bending moment at C is 0, and the bending moment at B is minus 20. Okay, therefore in order to connect C and B, you can use a straight line, and at a point D the bending moment is plus 40. So again, in order to connect B and D, we can use a straight line, and at the point A the bending moment is 0. Therefore in order to connect these two values A and D, you must use a curve. Now we have completed the bending moment diagram also, and in this case we can see that from C to this point B it's a straight line, and again from this point to this point D again a straight line, and from A to D it's a curve, it's a parabola. And again one more thing is that this point, this is the point where bending moment is changing its sign. So this point is called a point of contraflexure. That's all about this problem. Thank you.